they say that if you try to say that the question is basically covered. It's specifically it is comprehensive. Covers counting, algorithm, and also it is the first part, the proofs. We do have a proof. Yeah, so it is comprehensive. However, it is I restricted the problem, I restricted the applications to more list or function or graphs, right? So those are the contents, just the contents, different types. But the subject it is comprehensive. However, it's we place more say percentage, more weights towards the third part. The part after the midterm two. So that's a description of the nature of the problem. Alright, so that's for the first problem. The first problem is that given is a solid array C. Here this actually is decreased solid in the descending order. And C is positive. We want to find the largest index h such that CH is at least h. Indeed, this problem I can tell you is this backup. This problem actually is one problem is the real world applications, the h index. Have you heard of h index? Well, they say the publications or journal. H index is this C represents the citation. C represents citations. For example, I have like 100 publications. For example, some publication, some is a publication paper may receive like 600 citations. Some may receive 50, some 20, right? So it's my publication was sorted into decreasing order. C represents my citations of my works. And if I have 50 publications, which receive at least 50, I have 50 publications, 50 papers, which receive at least 50 citations, then my H index is at least 50. That is now it's about this very widely accepted standard used in evaluation. Promotion for the academic researchers. If you look at the Google Scholar, right? So the Google Scholar is they can find, right? For example, all of the H index of most of the professors, most of it is instructors. In this department. Right? Using Google Scholar uses H index give a rough, not accurate. Rough is performance evaluation of researchers. So we want to find the largest H. So this is H is decreasing. Could be right? Could be same value. That could be that. And then H is increasing. Right? This is H. And this is CH. Right. One part is the largest H. Here, this one. This is a couple of larger H such that CH is greater than H. Yeah.
Based on the time, I'm guessing we're going to use a binary search.
Of course. Oh, by the way, I corrected. In the original first version, I have A log N.
Oh, was looking
It's a log A.
Okay, I thought it might have been different.
Yeah, it's binary search.
Okay.
Yeah, if it's log A, I always think about binary search. So, yes, we will use binary search. And the last year is how do we solve binary search? Oh. Okay.
The first thing basically is we pick any random value like from like between one and n basically, and that will basically be the point at which we basically we then we check basically the current value basically.
Current value is where? You said current value. What is the current value?
The random value that we just picked from 1 to n basically.
Random value? No, it cannot be random value. If the binary search should be some.
N divided by 2, right?
Patrick?
You should you start by finding the midpoint of the array, and you check the value at the midpoint, and if it's greater than the index of the middle value, the index of middle, then you move the range of the search range to the right of the middle, and then you keep going until you find the value that satisfies.
If CH is greater than H, then you move to right, right? For example, if H is here, if CH is greater than H, then you have to move right. If CH is here, it defines it, you have to move left.
Yes.
Yes. Right, so actually, say, well, that's idea. But they say, in general, they say, whenever we develop some binary search, we should make sure that certain monotonic property exists. Because look at this our lecture on the binary search. We have this linear search for arbitrary list, binary search on sorted list. So here is actually we look at the CH minus H. This is like another array, right? Let's say that this is the DH. But let's say this is the rationale behind. DH, this is a difference. DH, CH is right there. H means DH is non-negative, right? DH is non-negative. DH is non-negative. What is DH? Monotonic? The difference. CH is decreasing, H is increasing. So DH is also increasing, right? So basically, if you look at this, we'll find this. We find this DH, right? And find the first one, which is drop to 0. This is the solid array. And we find the last one, which is non-negative, right? Last one, which is non-negative. So we use the property that this difference is monotonic, decreasing. So that's why we can apply the binary search. That's the most. I say if you write a solution or for any type of any binary search, you should provide brief justification, right? Justification that you have this kind of is a monotonic property. And you can search it because this array is monotonic, either increasing or decreasing, right? Either increasing or decreasing. And we found some ways which is non-negative. So that's why we can apply binary search. Any question? Yes? Okay, question? So, for any type of well, you can, from the past practice problems, you can see that it will modify the problem a little bit. For example, you will, for those kind of search, right, if you want to process, you need to ensure certain monotonic property, right? Certain monotonic, this difference. Alright? You can take a picture of it. Oh, if you, I mean, because this is the essential idea, right? So you say you have this monotonic property. Okay, you can come here. Oh, I can move here. But later on, where is it? That's fine. Take a picture. If no more question, I'll move on to the second part. The second part is the number of pairs, count number of pairs, such that AI less than bj, right? And we assume that this AI, that this A and B are sorted. So we have A and B. Same? Do they have same number? Not necessarily, right?
They don't have the same number, but they are both sorted.
It does not matter, it's already the circle. So one of M, the other one N. So we want, this is R, this is J, this is, those pair are counted if this is less than, right? They are less than.
I do know this one. This one basically, we basically use similar stuff to how we searched the matrix kind of stuff. It's because basically, because they're sorted, if any number in I that is lower than J, like at the current position, will be lower than every number beyond that one in J.
Right.
So yeah.
Right.
So if like A in position 0 is 1, and A in position well, A and B in position 0 is 2, then we know that that not only is 2 available, but everything else in the array will also be working for that number.
Okay. Yeah. That's why we can have we do not need to. I mean, there is a trivial solution. You just compare all the pairs, right? That's a quadratic m times n. But the reason is we can achieve the linear time m plus n is because of this this sorted property. Right, so here this actually is a 2-point method. It's more like this is like 2-point. Like is in the merge sort, merging of 2 sorted array. We maintain 2 pointers, 2 heads, 2 pointers. So we may have a pointer here, and we may have a pointer here. Right? 2 pointers. And for we will count the total number of pairs, right? That is the monotonic pairs. And what way that is for each j, it's just like what Michael said, right? For each j, we will count the number of the largest element, largest position in the first array, such that this this entry is less than this a red entry. Largest. So we start by J here. For the beginning, say if this is still less than this one, then move this point to right? And here we say we cannot move further. So for each J, we count. We need to find the I, the position of I, right? Such that the largest I, such that is AI less than BJ. Largest. So we'll keep moving the pointers here. So for each J, count is the number of I's. Such that is AI less than BJ. This actually is equivalent to the largest I. Such that. Because this is solid, we count the largest I. Right? So then say the number of pairs such an AI region is this I. So after this one counted, then we move the pointer for right. So then we move this to this one, right? J plus 1. Now you see we are still count the largest I. Then this I marked at least this one. So then you say we start from here. First you say move, right? To the right. Because the largest for this J plus 1, right? The largest I which for this entry should be say at least this entry, previous I. So then you say we should move this pointer right. Same philosophy as the merge of two sorted arrays. How it's just different how those 2 pointers are updated. And which parameter we count. So for each J, say rotate, we say move ahead of the first term. So we record this I, and all of the I's will be summed up. The summation will give us our solution. Well, so that's the argument. Well, we can also count, well, we just know we count for each J, number of I's, right? We can also say for each I, count the number of J's, which are greater than this one, right? We can also fix the I. We can also say fix I. But this is the J, the number of the position J which is greater than I. Right? So the other way. We fix I and move this J, right? You see, that's very similar to this merge sort. That's the general. Let's say that's the general category of the 2-point method. Question? Don't be shy of asking questions, right? Really say this is opportunity. So far, you say get the wrong answer or you say wrong approach, a different approach during practice. What do you think? The reason is that they say if now is have fully understanding of those arguments. if I slide modify, just like this is the previous steps, right? I slide modify the number, this is the setting, this you will be able to serve. Okay. I say the design is more important, right? We fix, we fix J, find the largest R, right? Like I fix one head of the second head, right? And then find the right possible head of the third processor. And then after that, we record R, right? And then we move J by one position. And then we update this R, the first part. This is one approach. The other approach is symmetric. You fix the I, or fix the point of I, and find this is the head of this secondary, right? It's like it's like alternative, right? It's a moving, shifting of the point. So the sorting, you can say that is essential, right? Well, I make it probably easier, you say, because I already assume that they are sorted. If not, you can have pre-sorting, have m of n time first, and then do those linear time calculation. Right. No question? Okay. Now we'll move to solo. The solo one is, again, we have two sorted arrays. We want to find sort elements which appear in both arrays. Yeah.
I had an initial idea of it, I'm not sure if it's correct, is it?
Sure.
So basically, we perform a looped binary search, in my idea, basically, we would go through each node in A, basically, so A1, A2, A3, A4, and perform a binary search for it in B.
Yeah, then in binary search, how much time?
So you take log n.
It's for each entry, like a fix B or fix A, either one, right? Fix A, and then say for every entry B, you find whether it is in A, right? And that's macro item. This is actually the first approach. There is another approach. So by the way, here the two arrays are not sorted after arrays. So you have to first sort it. I think Michael, I think that because you apply binary search, I assume that you have to first pre-sort them, right? Because otherwise you cannot apply binary search. Pre-sort the two arrays. That's fine. Because we have the budget of n log n, right? So pre-sorting is within budget. Right? Pre-sort the two arrays. Then say what Mark said you do the binary search. Now binary search here actually like they say you fix one array, Marker, that's right. Fix one array, you sort it, and the other one you check whether it is for each entry whether it is in the other, whether it appears in the other array, right? So for each entry it takes a log n time. So total n log n time. Okay. Oh, yeah, all right. Thank you.
Is A and B, are they sorted or unsorted?
Unsorted.
Unsorted.
But we just say unsorted is fine because we can pre-sort them. Because we have the budget of n log n time, right? So pre-sorted takes n log n time. You can so basically you can assume they're sorted. It's pretty right? Yeah.
So merge sort has n log n time. So would it be more efficient to sort them into one array or to sort A and B separately and then Because since they go from, 1 to n, both of them, they have the same amount of elements, right? So because of that, if you sort them, both of them separately, and you have a fixed index, let's say you start from 0 in coding, and then, you increment I plus 1 when you're checking, and since they have the same amount of elements, the indices should match in both arrays after you sort them. So is that the way that you can check whether they have duplicates? So pretty much check A0, B0, and if they're equal, you report that, and then A1 and B1, and if they're equal, you report that after you sort them.
You cannot just check AI, BI. There could be this one, this is, because it is, let's say this is 2, I can have this like 3, position 3, they could be equal. You cannot just check AI or BI. That's, if we just check whether it's AI or BI, this may say miss sort of common elements. Right? This may miss you cannot just check it's like vertical. You cannot just check it, right? It could be skewed. This entry is equal to let's say this entry. That's why I say I use bar search or there is other method. Not necessarily.
So the pointer at the beginning of both A and B.
Assume that's sorted.
Yeah, you sort of arrays, the pointer on both A and B. If the values of the two about indexes are equal, you increment both. If B's value is greater, then you increment the A pointer. If the A pointer is greater, then you increment the B pointer.
Right. That's smart. That especially if the arrays are sorted, it takes linear time. It's just like a 2-point method. If they're sorted, alright? After pre-sorting, then you just compare the heads, like a multi-sort, right? You just compare the heads, whether they're equal or not. Right? If they're not equal, if there is a not equal, there is a more, is a one head, one is a which one is smaller, right? Just like a multi-sort. Same as multi-sort, you just need to compare the ones which in the heads, right? Which are the equal now. Not the AI equal BI, but the ones at the current head equal now. So that actually is a smarter, is a faster algorithm if the arrays are pre-sorted. That will be linear time. So you see there is at least 2 ways, right? So Marcus has a way, say, like using binary search. And Patrick said, well, there is second way. We use, they say, the pre-sort, and they use the 2-point method in the scale, right? 2-point method. Both works. I'm glad they say you share those different ideas, right? That will be certainly helpful for your final exam.
Can you, is there any way you can merge A and B together and then check for duplicates, so I and A plus 1 are equal to each other, and then you iterate throughout the array?
Yes, you can also merge them into a single sort array. However, the sort array has maintained a record. For each entry, you have to maintain record whether it is the entry is in A or in B. Because you may have 2 entries which are same, but they both appear being A or B. Right?
That makes sense.
Then you have to maintain, say, additional auxiliary information. That's fine, right? You can do that. But it will be easy. We can skip that. Yeah. It's like multi-sort, right? We can do it.
Right.
Before it's like in the merging phase, right? We just compare the two under the current head, right? Whether they're equal or not.
Would it work if let's say one of the conditions for the arrays was that there cannot be any duplicate numbers inside of the arrays. So like you cannot have 2 ones in one array, so you can only have one.
Yeah.
Let's say kind of like a set. So if you find 2 ones, then that means that one has to be from A and another one from
Yeah.
B.
But here is we do
Right.
not assume that A and B is distinct, right?
Yeah.
Yeah. So that way is more general and simple. You don't, this way is a, the two-part method, you don't need this like additional array. It's actually called, the one memory, constant memory. You don't need the additional like array. If you want sort of have to allocate this like octal array. I summarize 2 methods. One is binary search by Michael. I also want to emphasize, you only need to sort one array. Right, Michael?
Yeah, you only need to sort of ones.
You only need to sort one array. You don't need to sort both arrays. Right? The second one is the Patrick method. It's a 2-head. This one is potentially faster. Because this is in the set up with the pre-sort, both need the pre-sort, right? With the pre-sort, this is you run a linear time comparison. This problem is also similar to the homework from home 7, but this is whether this is mapping is injective or not. Right? Similar. Whether the function is injection or not. Right? Injection, if it is injection, then there is image, it should be distinct, right?
I don't, I think I have the answer for 4.
For this one.
Yeah, for the,
Term 4?
yeah.
No, we have not. Now we'll move on to this.
I got this.
But it's important for you to understand design. Why is it correct? Why is it correct? Because I said you will not see the exact same problem in the exam, right? But the analyze is equal. That's it. Problem 4? No question, right? Any question for it now? For the problem 3? No? Problem 4.
I think I got it.
Count number of topological orders in this one. I say already make this clear. These 2 solid circles that this is the source, unique source, this is the unique thing, right? The white node here, not this is source need or thing.
There's, yeah, it's.
So there is a source should be say we start with this node, black, and end with this black node. So it's, we need to count the orders of those white nodes.
The problem is that, yeah, like each of the white nodes could occur potentially at least a good number of different possibilities for when they could occur.
So this one can appear before or after any other node, right? However, this one must appear before this one.
Yeah.
So requirement is that you say for an order, for all of, I mean, we have 3 groups across 3 paths, right? 3 groups. For nodes in which each group they have to be solid. Right? We have 3 groups. We have 2 nodes, first group, so 3 nodes in second group, 2 nodes in the third group. The requirement that is those nodes have to be solid. Those 3 nodes have to be in the solid order. And those 2 nodes will be solid order. That's only requirement. Right? For the topological order. So how many say order? This is a counting problem. This is the problem. This is from the second problem. middle ground.
Yeah, the total possibilities, I do know this one, it's 7 factorial. The total possibilities, we have to remove them.
Yeah, but how many, that's the 7 factorial, but we want is to count how many of them are logical, right? Right. We have 7 nodes. We have 7, all possible orderings, 7. But among them, how many of them are logical? Solid. Anyone would like to share your answer? It's not difficult. You can immediately get straight or apply the counting rule we learned. I said this, I keep this in the simplest part for the electronic exam. Jack? Try. It's fine, it's wrong, right?
Oh, I'm not sure.
That's fine. Even if it's correct, fine. Okay.
I got 210.
Yeah, but how do you count it? I said the number is not, maybe it's, I didn't count the, it said the value. I know how to count that. Also, I just want for, expect from you. Yeah. How do you do it?
I got it by the number of topological orders for like a tree is equal to the sum of the topological orders by removing one of the source nodes. So you like remove one of the source nodes and count how many topological orders there are with that graph, and you do that all the way down.
Okay, so, well, you move to here, this one can move to N of 3, right? It has 3 probabilities. But from here, how many probabilities? This is the first one, the next one, how many possibilities? You have learned. The idea is, well, let me reinterpret this, right? We have 7 nodes, right? We have to select 2 positions for the first group. We have to select, we have, let's say, we need 9 ranges, right? I need to place this 1, 2, 3, 4. 7 is a 0, right? I need to place those 1, those 7 into the 0. Right? So I need to pick 2. Let's say 2 for the first group. Right? I need to pick 2 for the first group. And I also need to pick 2 for the third group. I also need to pick 2, right? Just pick anyone. This for the third group. And remaining 3 for the middle group, right? That is the translation of this topological order. Pick 2 for the first group. Pick another 2 for the third group. And remaining 3 should be the for let's say the middle group, right? That's it. So this is what? This is the multinomial coefficient of subset split rule, right? Subset split rule. So how many of them? We have 7. We have 2, 3. That's it. This is equal to 7 factorial over 2 factorial, 2 factorial, 3 factorial. Let's see what's the number is. I didn't calculate. So this is 7, 6, 5, 4, and then 2 times cancel 3. So that is 2. That is another 210. It's about 210, right? Same answer, right? Maybe they give the, I'm not sure it's how you get the 210.
7 times 6 times 5.
Oh, yeah, but it's at the beginning, it's Patrick said the answer is 10. But I'm not sure how you get it. This is, right, it's the same answer.
210 is the answer.
The key is that they have to translate, I mean, those about order in this selection plot, right? In the selection plot, we select select is the position for each group, for each path, right? Here is we have 3 paths. Select the positions for each path. This is clear, right? Jack? Clear now? Good. Any question? Guys, if I just what I said, if I verify the problem slider, you know, how to calculate, right? That reason the most important is that how to translate the ordering into this selection, right? Alright, so we still have 3 problems left. Problem 5 is another counting problem. However, this actually is a combination of counting problem, the second part, and topological ordering, the third part. Yeah, this is another counting problem count that is in the passes. That from a source S. This is a unique source. This is a unique source. Count is the number of passes from every S. So that's all those big. So I will give the hint. For all those 3 problems, I'll give the hint. Here we need some kind of recurrence. This is likely the second problem. We need the recurrence And well, for the recurrence today is our case case, we need to consider topological order. So for topological order is a complete linear time, right? So this is fine, it's within our budget. And then for we need consider is the recurrence. Take a picture of this. I can read this. Right? I can read this, right? Fine. So we have topological order. Let's say S V0, V1. Let's say V1, V2, V8. Right? This is topological order. And then say we look at it, say the FV0, the source is called 1. From S to F0. Only one path, the Fourier path, right? Now let's look at FVJ. What's the number pass from S to Vj? The path from S to Vj is a must enter from some node Vi, where I is less than j, right? This is a path. The must enter from some neighbor, neighbor. Vi, where I is less than j. Because this is a direct integral. So Fvj is equal to Fvi, I is less than j, and Vj are never. That's it. Right? So then we calculate the FVI's, right? It's this order. It's linear time. What order linear time? Here we calculate this along every edge, right? Along every edge. So again, it's linear time. Question? Yeah. No. Using what? DFS or BFS?
DFS.
No. We don't need any DFS or BFS. We only need the topological order, right? This is the only part we need. Topological order. And then we calculate this first one is 1, right? This is a recurrence. This for j greater than 1. That's a recurrence. So we start this from j from 2 to n, right? Okay. Good. So I'll move on to the next one. Although if you still have questions, I'll stay here after class because there is like a individual discussion. Problem 6. This actually is a proof part. Today, I'll say this covers the first part. So we have is a algebra P, right? It has 8 nodes, and among them, 2 nodes S and T. there have a path, there is the length is greater than half of n. The short path length, number of edges, right? The short path length is greater than half of n. Then we say that is we can remove some nodes V, right, other than S and T, such that after this removal, then S cannot reach V. This is the proof part. And basically they use some kind of pigeonhole principle, I would say that. However, it does need some graph for short paths, right? This application context. Anyone would like to give a try? Alright, I really don't like to just argue the solution here, but because if I just give a solution, then it's just another lecture. And then well, we already have learned hard lesson, right, before. It's not practice, and then slot chain problem, then you lose the idea. It happened in the first midterm. First midterm, if you look at problem, I change the number from swap number is 330 and 224. When I swap the numbers, there is some of it is good. And for the second midterm, I use the functions. There is another interpretation of replacing is like ball into pins. Let's not change this in the interpretation part. Then if you do not practice, then you will lose. Okay, this is the idea. I'll try my best. That is what makes the problem. This is the best feature best. So for this one, the problem 6. I'll give the hint, DFS layer, right? We have S here, and we have T here. Let me the other layer too. But this is, if you look at the DFS layer, right? And what we know that the number of layers here is greater than half of n. Now, actually, the distance is greater than half of n. So the number of layers for this half layer plus 1, right? So let's number n must be at least 3. N must be at least 3 because, well, first n must be at least 2. Because we have two nodes S and T, right? N cannot be 2 because we have S and T have a path of length half of greater than half n. If n equal 2, then the length is equal to half of n. 1, right? If one are two nodes, then their length is 1. This will be half of n. So n cannot be equal to 2. So n must be greater than 3. This is from the assumption, right? Now how many is the intermediate layers here? At least half of n minus 1. Right? Number of intermediate layers are layers between S and T. At least it's more than half of n minus 1. how many nodes that can appear to those layers? At most, n minus 2. Exclude S and T. So the number of nodes here is the number of nodes, the total number of nodes here is less than equal to n minus 2. And this actually is equal to half of n minus 2. Right? So we have at most n minus 2 nodes appear in more than half of n minus 2 layers. So, but also every layer has at least one node, right? Because of paths. Every layer has at least one node. Then by pigeonhole principle, at least one node, one layer, has exactly one node.
And then that layer is basically the one that will.
Yes.
So basically, yeah, then I just realized how we can detect it is we do basically a breadth first search until we eventually run into a situation where
Right. Yes.
we basically get like one. I think it's
So on this one, we have only one node width.
Yeah, so it would be so like using
Only one node width, right? By the pigeonhole principle. Right? We have more than, we have at most half, we have at most n minus 2 nodes, and distributed on more than this number of layers, more half layers, right? And each one layer has this one node, because there are path from that. So some layer has that one node. And we remove that node layer. The whole layer, there is the path. Is that difficult?
I actually figured, at least I think I got, so like basically one way you could do it is basically, so using the standard where we have a stack basically which records each one that we added, or queue, yeah, it's queue that's used in that.
Do not use any algorithm.
Oh, no algorithm?
Because, yeah, there are no algorithm. You just say they exist or not. We just prove that they exist. This is a proof problem.
Oh, we just need to prove that it exists.
Yeah.
Okay.
You don't need to say actually find it. But from this way, you can find it now. Find this is some layer like this one node. You can find it based on this structure. That's a proof. Pretty clear, right? Yeah, fine.
Is there anywhere you can draw a graph to make it more visual that represents that example, or one of the examples?
This is like example, right? You just add whatever age is here.
Okay.
But whatever age is between, right? Layers.
Oh.
The age are not, I mean, specifically, that means the importance that is, there is a layer which consists of one node. So one example, I said, you just add edges.
Any edges you want, and
Any edge you want.
it'll still be true.
Yeah.
Okay.
Yeah.
As long as it meets the one condition.
Yeah, well, condition that less from the past, that is more than half of n. So for this kind of proof, use a pigeonhole or using the simple conjugation. And I'll give the hint, right? So you should be prepared for this kind of problem. Especially give the hint. Any more questions? Now this is we'll move on to the last problem. So last problem is about the construction of the state transition machine. Right? So here is we have your graph, and some nodes are colored red, some are blue, some are uncolored. And a balanced walk is like it is a balanced synthesis, right? Like balanced synthesis. Because they say for every prefix, the number of red nodes and the number of blue nodes differ by at most one. In other words, either same number, or one more blue or red node, or one more red node, right? So that's called balanced walk. They have same concept as balanced synthesis. Yeah.
I have to leave early. Can I sign the attendance sheet?
What?
I have to leave early. Can I sign the attendance sheet now? For Thanksgiving.
Well,
Like I have to.
you don't need our market.
Thank you.
Because I don't want to interrupt this lecture. So this is like the balanced synthesis, right? And we want to check whether there is balanced walk from to a node S to a node T. So this is standard type of control, or is a constraint walk. It's like it's in the French flag walk, right? We have this kind of requirement, The key for the problem, well, the linear time average, the average itself is simple. There should be some kind of BFS. You see, for that problem, you see, the key part is the construction of state machine. And I already give the hint. That's actually, this hint was critical. Without this hint, you might think, spend a little more time, right? But with this thing, then it should be easy. That's the thing. So we define the state from this product. This is the same as we have done before. Product construction. For each node V, we have 3 states. Right? We have 3 states. For each node V, we have 3 states. V0, V1, V minus 1. And the second entry, as a hint, it represents the balance, the red minus blue balance. That means at any time, if we follow this balance walk, right? What's the balance of the difference?
Get it at most 1, right?
Yeah, at the most 1. Because difference at most 1. So it is 0 means we reach this node V with equal number of red nodes and blue nodes.
Right.
The balance, the second entry is 1 means we have 1 more red node.
And if minus 1, 1 more blue node?
Yeah, minus 1 is 1 more blue node. That's why called red minus blue balance. Naturally, you should get that, right?
That's
because that is the constraint. The variance should be at most 1, right? So that's the 3 states. 3 states from every node. We have n node, we have 3 x states. That is the hint. And this hint actually is most, I think, most important. And then transitions. The transitions actually is relatively easier. Relatively easier because right, we have this. So we consider is every edge UV. Right, we consider every edge UV. then every edge UV will induce some kind of transitions. We consider three possible cases. Case one, V is uncolored. Case two, V is red. Case three, V is blue. Right? And we consider all possible transitions that can be induced by every edge, right? If this V is uncolored, then from U to V, balance will not change, right? Balance will not change, because V is uncolored. So basically, it is U I to V I. Balance does not change. I is from there for all of three possible. Now if V is red, V is red, how the transitions can be, yeah, Patrick?
VI to VI plus 1.
Right. Well, I plus 1,
And if it's VC or VI, either way.
UI to VI plus 1, because we have one more red, right? What is I possible? I plus 1 cannot be 2, right? I can be
0.
0 and
-1.
negative 1. Here is 3, right? 3 states, 3, and here this is for I, 0, and minus 1. Right? We cannot have from already red, we already have a balance of 1, and move to another red node. That's not allowed. Intuitive? That's true, right? Yeah, so Patrick gave this is the right transition. Now I say, anyone give me the last transition from a node U to a blue node. Jack, now.
UI to VI minus 1.
Right, got it. UI to VI minus 1, because if we at the blue node, the balance dropped by 1. Now, what possible I allow here? 0, 1. Great. So for every edge, we introduce at most 3 transitions, right? Either 2 or 3. So then, in the step transition here, we have linear number nodes against the OM number nodes and OM number edges, right? Then reachability just from reachability of the existence of one is equivalent to from S0 to V0 or V1, V minus 1, right? Just reachability. If V S0, this state can reach any of those 3 states for T. Can reach any of those 3 states, then there is a balance 1.
Right.
Right? Alright, so that's all for the sample solution. I think we're almost run out. We're good. So I will not go through the lecture 16, right? The crypto. You can just check this slide. And about this is the finite the grade. In addition to this is for the finite homework score is drop the lowest, right? And also is the piece. I think now is we're clear on the issue. Or the only one for this is the course participants, for the attendance, right? I have our record, and also they also have other records. We'll put together, and we have 5 points, right? So I believe most of you will get 4 points. But if someone like miss like 20% of lectures, I'll give 5, right? Miss 120, then you can slow down, drop to like 8, 4, 3, 2, 1.